So let's go back to this PPT again and look at radiative forcing and temperature. Okay, so this is again a annual mean and solstice incoming radiation. So the annual mean is shown here. This is insolation, which is the incoming shortwave energy from the sun. Remember the energy balance we did in the second chapter. So it has obviously less radiation averaged over a day or a year at high latitudes, and maximum energy is received in the low latitudes. If you look at solstices, so 21st December and 21st June, so this is the Boreal winter solstice and the Boreal summer solstice. Solstice is basically where the day is the shortest during the winter and the longest during the summer, right? So you see that the winter, obviously sun is in the other hemisphere, so the northern hemisphere is having a winter, so the radiation disappears at the polar circle, and north of it we will see that you will have diffuse sunlight for all winter long. And the southern hemisphere is obviously having summer, so it maximizes its radiation at the poles, with a little dip here, which again has to do with the polar circle, where the length of day becomes the key. It becomes the edge of the polar day, as the caption says here. And you get similar effects here during the summer solstice, when you have the northern polar region getting 24-hour daylight, so having maximum solar radiation, with the dip at the edge of the polar day, and then drops off into the southern hemisphere to the polar circle, and you get complete darkness in the winter hemisphere, right? So basically they're almost symmetric, but you can see there is some asymmetry because of the distance from the sun being not the same during the two solstices, as we will see in a minute. So here is solar flux coming in parallel to the sphere, because sun is far enough out, 150 million kilometers, and the earth is tilted to the plane of the ecliptic at 23.5 degrees at the present. This changes from 22.5 to 24.5 on a time scale of 41,000 years. And you can see that during the summer pole, the radiation is distributed this way, where you have darkness beyond the polar circle here, and daylight beyond the polar circle here. So this is what gave us the dip at these latitudes of the polar circle. Okay, so the summer hemisphere is getting radiation, and the winter hemisphere is pointing away from the sun and receiving less radiation during its winter. But the axis is elliptic, it's not circular. So right now in the current configuration, the perihelion, or the closest pass to the sun, happens just after the winter solstice of the northern hemisphere around January 3rd. So we are actually closer to the sun by a few million miles or kilometers during our winter in the boreal summer, which means the winter should be a little bit milder, not a big change, but nonetheless. And during our summer, we are actually passing through the aphelion after the solstice, and that should make the summer a little bit milder. So we end up with these equinoxes where the sun is overhead on the equator and the length of day is the same at all latitudes. So you have the autumnal equinox and the spring equinox, and this orbit itself precesses on about 23,000 year cycle, because of a combination of the wobbling of the Earth itself around the axis of rotation, like a top that wobbles when it slows down, the precession, and because of the gravitational pull of the other planets, the equinoxes themselves also precess. So obviously the calendar has to be adjusted as the equinoxes begin to shift, and the calendar cannot remain the same. If the apsidal precession, it's called, moves the dates. Okay, so we will look at how the seasonality, the tilt, and the distribution of radiation and the energy balance that we talked about before, without looking at the latitudinal distribution, how they are balanced on these zonal mean meridional sections. Okay.